Welcome to another tutorial, 3G 4G tutorial. This time we are looking at radio frequency, band and spectrum. Before we begin, I should actually warn you that this video provides a very simplistic explanation for a really complex topic. I'm going to omit some details to keep it high level, and it's also a bit boring in the beginning, but hopefully it will become interesting later on. So what exactly is spectrum? A spectrum, which is singular, plural is spectra or spectrums, is used to classify something on a scale between two extreme points. So for example, in our daily life, we refer to as the political spectrum, which consists of left-wing parties, extreme left-wing parties, and extreme right-wing parties, and a lot of different political parties in between. We also have the socio-economic spectrum, which in UK it comprises of working class, the middle class, and the upper class. In this video, we will look at radio spectrum, which is the part of electromagnetic spectrum. A very simple chart which I found from Google search, of course, a chart from Sura, and this chart shows electromagnetic spectrum, the whole of electromagnetic spectrum. Now there are quite a few different charts. If you just search electromagnetic spectrum on Google, you can find quite a few charts which explains this very complex topic in different ways. I recommend that you actually do this search and see which one suits you best. So what exactly is an electromagnetic wave? Um, Electromagnetic waves that compose electromagnetic radiation can be imagined as self-propagating transverse oscillating wave of electric and magnetic fields. So in this picture you can see the electric field is the vertical one, which is blue, and magnetic field is the horizontal one, which is red. And what exactly is frequency? Radio frequency is an electromagnetic wave using alternating current. Frequency is something that happens over and over again and again. It's very frequent, consistent, and repetitive. So, frequency is a number of times a specified event occurs within a specified time interval. A standard measure of frequency is hertz, which is the number of cycles per second. If you look at this picture, you can see a wave, an alternating current wave, which goes from 0 all the way up, comes back to 0, goes down, and then comes back to 0. So this wave goes up and down, which completes one wave in a second. So it's got a frequency of 1 hertz. This wave, which it does this uh, it happens 5 times, the cycle happens 5 times in a second, so it's got a frequency of 5 hertz. The electromagnetic spectrum is a collective term which is used to refer to the entire range and scope of frequencies of electromagnetic radiation from 3 hertz to 300 exahertz. So exahertz is a very big number. I put a lot of zeros to show how big exahertz is. And depending on what source you read it from, some start rather than starting from 3 hertz, they start from 30 hertz or 300 hertz, right? And some of them only go to around 100 exahertz. So this is sometimes these things are different depending on different sources, but let's not worry too much about it. So we saw hertz. 1000 hertz make a kilohertz, 1000 kilohertz make a megahertz, 1000 megahertz make a gigahertz. Some people pronounce it as giga, but I think the correct pronunciation is giga. And 1000 gigahertz make a terahertz. Now 1000 gigahertz is a very large number for this presentation. So generally we will look at megahertz and gigahertz in this presentation. So looking back at this electromagnetic spectrum chart, the radio spectrum is a part of spectrum from 3 hertz to 3 terahertz, right? Now in this particular picture, it's shown from 3 hertz to around uh, 1 terahertz, right? But or less than 1 terahertz, but generally it's up to 3 terahertz. Again, as I said, depending on the source, you can have different information and different values. So what is a frequency band or a spectrum band? Bands are group of frequencies defined to make it easier to remember, and bandwidth is the difference between maximum and minimum of any defined or undefined band. So let's say if we had a band which goes from 700 megahertz to 800 megahertz, the bandwidth of that band would be 100 megahertz. Larger bandwidth means more data flow. So the way you can imagine is you can imagine the bandwidth as like pipes carrying water. So the more bandwidth means the fatter pipe and the more water can flow through it. Wavelength. Wavelength, generally written as the Greek letter lambda, is the distance between similar points on a back-to-back wave, on two back-to-back waves. It is calculated as c divided by f, where c is the speed of light. So for 1 megahertz, the wavelength would be roughly 300 meters, and for 1 gigahertz, it's roughly 30 centimeter. Now, wavelength is something very important which we need to remember, because we will use wavelength when we want to calculate the length of an antenna. So looking back at this electromagnetic spectrum chart, you can see for 1 gigahertz, the wavelength is 1 feet. So the frequency, the wavelength is the first horizontal measurement, and then you have frequency is the fourth one. So for 1 gigahertz, it's roughly 30 centimeter or 1 feet. And if you go up, so when you go to something like 100 gigahertz, the wavelength becomes really small, like 1 millimeter. And please remember this, we will use this when we are looking at 5G. Phase is the same frequency, same cycle, same wavelength, but two or more waveforms when they are not exactly aligned together. So phase can be measured in distance, times, or degrees. So if you look at this, there are two waves here, but the second wave starts is 90 degrees offset from the first one. So basically we will say it's 90 degrees out of phase from the first one. Similarly, in this one, the two phases are 180 degrees out of phase from each other. And it is important to see what effect the waves have. Now, why would waves get have different phases? So when something is transmitted, right, you can have a direct line of sight, but you can also have a wave which is going through different paths. So it's get reflected from a building or from some kind of a car or something, and it arrives out of phase. Of course the waves would be slightly different in amplitudes, but let's not worry about amplitude right now. We will look at it in probably next couple of slides or something. When phases arrive, when two waves arise at different phases, as you can see, the pink wave in here is the result of two waves being out of phase. So you can see sometimes it basically the two waves cancel each other, and the resultant wave becomes zero, whereas sometimes the two waves are in the same phase and they add together, so you have the resultant wave is even bigger than the original. So you have to remember these things. And uh, the mobile phones, they have to be designed in such a way that when you have these multiple waves coming out of phase, they don't cancel each other but they add to each other. So this is again another complex topic which we are not going to look at in this particular video. So what exactly is amplitude? Amplitude is the height, force of power of the wave. So the greater the power, the more the amplitude. So when I'm speaking, if I speak loudly, it means it has more amplitude. If I speak slowly, without much amplitude, then you can hardly hear me. So Amplitude is you can think of as the power of the wave. And I often see people asking like, oh, how is amplitude related to frequency or wavelength or phase? But so there is absolutely no relationship between frequency, wavelength and phase as with amplitude. So amplitude is completely different thing as compared to frequency, wavelength or phase. And I mentioned earlier that antennas are related to wavelength. So generally it is said that antenna should be half wavelength or lambda by 2 for perfect reception, but they can be as low as lambda by 10. So to give a comparison, the car on the left hand side, so these are both the same cars, the same brand of cars. The car on the left hand side has got an antenna for FM radio only, which is 88 to 108 megahertz, whereas the car on the right, it not only caters for FM radio but also caters for the digital DAB radio, which is 175 to 230 megahertz. Now again, this is a very simplistic explanation because in reality the car on the right has an active antenna, but this is completely advanced topic, so we won't look at it now. For TV, some of you may remember using rabbit ears antenna, the one on the left, which is optimized for receiving VHF signals from 30 to 300 megahertz. And again, it should be with a very good quality high amplitude signal. Whereas the one on the right is it can catch a lot more frequencies, not just the VHF but also works on a higher frequency, and it can also work with poor quality signal. The way it's designed is it works as a magnifying glass. So when the different frequencies arrive, it basically amplifies them and it makes them more easy to be received on a TV. So a question which I often ask and which often gets asked in different fora is whether low frequency is important or high frequency is important, and this question is more from a mobile technology point of view. So whether the mobile technology, particular technology, should use low frequency or high frequency. So if you have higher frequency decays faster. So if let's say if you have the same and same place from which you have two different antennas, one for low frequency, one for high frequency, and you are transmitting at the same power, the low frequency will go much further than the high frequency, right? Here I am showing example of 900 megahertz and 2.1 gigahertz. So the 2.1 gigahertz decays much faster than the 900 megahertz. At the same time, you have to remember is a cell has a certain capacity. So the more users are there in a cell, that means uh, so the lower the frequency, that means the more number of users, and it means everyone is getting lower data rates, right? If the cell size is smaller, that means there are less users, and that means everyone is getting higher data rates. So again, in this particular case, you can think like, okay, you know what, higher frequency means I can get higher data rates. Higher frequency gets reflected from walls and has poor penetration, whereas lower frequency uh, gets attenuated but it still penetrates. That's why some of you may remember that the original GSM frequency was GSM 900 megahertz. It performed much better than the other frequency, which was 1800 megahertz, right? Because 1800 got it decayed much faster, right? And it had poor penetration capability. So this is slightly older chart, but it basically shows the cellular spectrum which is used in different parts of the world. As you can see, the 900 megahertz is mostly used for GSM, right? Initially 900 and 1800 were used mostly for GSM, the one in the blue. But then most of this 1800 megahertz frequency has been refarmed. That means people have started reusing it for 4G. So this chart doesn't show that, but most of the 4G frequencies throughout the world is 1800 megahertz band, which is also known as band 3. Similarly, you can see most of the world has 3G on 2100 megahertz, which is the one in green color. Of course, you have some of the other frequencies being used for 3G, but the most common frequency for 3G is 2100 megahertz. That's why 3G was sort of quite poor in penetrating indoors. So when you were indoors, you might receive GSM, but you might not receive 3G because of the frequency was actually very high. So just to give continue with our example of antenna. So this is an old GSM 900 feature phone, and you can see that initially the antennas used to be sticking out a bit because for 900 megahertz you still have slightly uh, larger antennas to get better reception. Uh, and for Wi-Fi, so most of the Wi-Fi frequency in the world used to be 2.4 gigahertz. So Wi-Fi was sort of a universally same bands of frequency being used throughout the world, which was 2.4 gigahertz. But now you also have the 5 gigahertz band which is being used, uh, and but the 5 gigahertz is not completely aligned in different part of world. So there are some overlaps, and then there is some unique frequencies in different parts. There is also a 60 gigahertz Wi-Fi frequency, but you won't find them in your laptops or your phones because of such high frequency. It attenuates very fast. It's known as Y gig. So if you see Y gig anywhere, it's basically the 60 gigahertz Wi-Fi. And this is just an example of iPhone 4, because our smartphones have to handle a lot of different kind of technologies, radio technologies. So it has to have antennas, and it should be in such a way that it doesn't stick out. So the iPhone 4, the one on the left is the one which was used in most part of the world, but in US you also had the 3GPP2 CDMA standard or EVDO. So you had the one in the red, as you can see the antenna on the red on the right hand side. uh, so this is just to give an idea, and you can see the Bluetooth, the Wi-Fi, and the GPS antenna are just very small. This is from the one Samsung Galaxy S8. I'm not sure if it's been released at this time or just about to be released, but just to show an example of how different kind of antennas are in this particular smartphone. For 5G, now because we are sort of running out of spectrum in the lower frequency bands, for 5G, there has been a lot of discussion on what kind of frequency should we use for 5G, because you want to have very large bandwidth to be able to deliver really high data rates and some of these innovative services for which 5G is being touted. So to have this really high bandwidth, you have to go at higher frequencies, and generally the frequencies above 30 gigahertz is known as the millimeter wave, because the wavelength goes in millimeters. So there are a lot of proposals, so different regions had different proposals for frequencies, and you can see the one at the bottom are the bands being studied by ITU for 5G. But then there are also some bands which are not actually listed here. For example, in America, in the US, they are using 28 gigahertz band to test the feasibility of 5G. So but for 5G, we are going to go and use a much higher frequency in addition to the lower frequencies. The way I show it is, I say that there are going to be three different layers which will be used for 5G. So the one which is less than 1 gigahertz, or in some cases it would be less than 2 gigahertz, which would be the coverage layer, right? Because we saw that the lower frequency means it goes much further, so it would be the coverage layer. Then you would have the capacity layer between 1 and 6 gigahertz. right? And in this capacitor layer, which is the same like LTE frequencies nowadays mostly, so you can give like higher throughputs, whereas in the coverage layer, because you won't have enough bandwidth, you won't be able to give higher data rates. So in the capacity layer you can get higher data rates, and then you would have high throughput layers, which is between 6 gigahertz and 100 gigahertz. Generally people refer to them as millimeter wave, but millimeter wave generally means frequency above 30 gigahertz. So below 30 gigahertz, you can call it centimeter wave, but generally you would see people refer to the whole 6 gigahertz to 100 gigahertz band as millimeter wave. um, so these high throughput layers would generally be quite small, and it it can give, like, you can get really high data rates in this high throughput layer. So the expectation is like you can get easily 1 Gbps, when on an average each user should get 1 Gbps, or maybe at least 150 200 Mbps. But you can get 152 Mbps with technologies called with a technology called gigabit LTE, which is either available today or will be available soon. So because of high frequencies, you can put the antenna size. Remember, higher the frequency, the lower the wavelength. So the lambda by 2 goes very small. So this is an example from a Samsung presentation, and it shows that you can have 32 antenna elements, like, because each antenna element is so small. So this is in 28 gigahertz frequency band. You can have like a 16 element array on the top of this phone, and 16 element array at the bottom. Now remember, this would be in addition to the already existing antennas, which, because your phone will still have to support 3G, 2G, 4G, Wi-Fi, Bluetooth, GPS, right? So you would still have existing antennas, plus you would have this new antenna array. So this is one of the advantages of millimeter wave, because you can have more antenna elements and you can actually get better reception. Plus you can do something called beam forming, so which is from the base station. So the base station will again have a lot of antenna elements. This is just one of the pictures from an IEEE magazine, I think, and it shows that there are lots of antenna elements at this particular base station. And what these antenna elements allow you to do is they allow you to create a beam. So each of these colors you can see is a beam, and when you create a beam, that means you can focus all this energy uh, into one particular UE. So each UE will sort of get its own beam, and it can get like high data rates and very reliable coverage. So there are a lot of different possibilities with 5G and millimeter wave. So that's about it, what I wanted to cover in this particular presentation. Hope you liked it, and please leave your feedback in the comment section. Thank you.